So let me start. We had discussed the Levi-Civita connection yesterday, and the main point was it is uniquely fixed through the metric. You give the metric, you have a particular formula for it, which was just this one, half G alpha sigma d mu G sigma nu plus d nu G mu sigma minus d sigma G mu nu. And through this connection, we can define the parallel transport of vectors and also the geodesics. So what I am going to do today is do an example of this machinery. And it will also introduce a particular method which I haven't really discussed in theory, but it will be clear what I'm doing when I do this method. So what I'm going to do, I consider that I have a sphere in three-dimensional space, three-dimensional flat space. And I'm going to induce a metric on this. The philosophy which we have been taking is doing things directly inside a manifold. So what in principle you could have is that because this sphere is a two-dimensional surface, you have some coordinates, let's say theta and phi, and you are given some metric. Now, how do you know that it's a metric of a sphere? Well, we will discuss those things later, that how do you decide that you are in a curved space and what kind of curved space. We haven't really discussed that right now. So what I could do is give you a metric and tell you out of my head that this is a metric for a sphere, a two sphere, and then work out the geometry, some of the geometry of it. But instead, I'm gonna do some other technique and sort of derive this metric as because form the embedding of the sphere inside the three-dimensional flat space. So three-dimensional flat space has a flat metric which induces a metric on this surface. Now, if you are given, the problem we face is that if I'm given a metric, like for example, suppose it's a two-dimensional thing. Well, let's write it this way. It doesn't even have to be two-dimensional, and in any dimension. How do I know that this is not a flat space? Because we have seen that we are allowed any kind of funny coordinates. And in funny coordinate systems, these coefficients, they can take any kind of crazy form. So if I'm given a metric, how do I know that it's flat or not? That we will discuss later. But for now, this much is clear, that if I have a coordinate system where this metric takes this form, the Minkowski form, for the Lorentzian manifolds, or this for this Euclidean form for the Riemannian manifolds, then we know, and it's a global coordinate system. This covers the whole space. Then we know that we are in flat space. So if we can find a coordinate system where the metric takes this form, then we know that we are in flat space, because the flat space has this metric and it has whatever the geometry you derive from this metric is just the geometry of the flat space. But the other way around is not true. If the metric, if you are given a coordinate system and it has this funny form, you don't know if it's flat or not. One thing you could do, you could try to guess a coordinate system where this metric goes to this. If you are succeed in that, then you know that you were all the time in flat space. But as you can imagine, it would not be that easy to guess such a system, such a coordinate system, and it would even be harder to prove that no such coordinate transformation exists. So we will in general need some other method, some intrinsic method that without any reference to a coordinate system, we should be able to say if a space is curved or flat, and if it is curved, how much it is curved and in what sense it's curved, how to characterize the curvature. So that would be, we will encounter Riemann curvature tensor, which characterizes the curvature of the manifold in its complete sense, but we won't discuss it today. But this is just a remark that the flat metric, we can tell if a space is flat if the metric is flat, if the metric is this one or this one. But the other way is not true. क्या क्या इशू है? Excuse me? Hello? Can you guys hear me?
Yes sir, हम सुन सकते हैं आपको.
So someone said there's an issue. What's the issue?
सर मेरा ख्याल है आपकी तरफ से आवाज आई थी.
नहीं, मेरी तरफ से नहीं आई थी, ये किसी और की आई थी. Anyway, I think it was someone unintentional thing came in here. Okay, let me go on. So I have this, I start with the flat space, flat three-dimensional space. So, and in Cartesian coordinates, the metric is, I can write it like this in the shorthand. So this is the flat metric. And because we now know that the geometry is all encoded in the metric, so if the metric is the usual one, then it's a flat space. But I can change the coordinates certainly. So consider spherical polar coordinates. So how do they look like? You all know it, but just let me put it as a reminder. This is X, Y, Z. These are the Cartesian ones. Then you drop, if you take a point whose Cartesian coordinates are X, Y, Z, how do you assign it the polar coordinates? You count the angle which you make as you come down, as this vector comes down from z-axis to come meet this point xyz. You count that angle, and then you consider its projection in the xy plane, and then you count this angle phi, which this projection makes with the x-axis. So with this thing, then it's clear that what would be x? You take this projection, so it's going to be r sine theta, because the projection along the z-axis is r cos theta. So the projection in the perpendicular plane would be r sine theta, if r is the length of this vector. So x is, this is r, this length, r sine theta, and then the x is equal to the projection of this on the x-axis, which is just cosine phi. And y is again r sine theta and projection along the y-axis, which is sine phi. And z is simply projection of this vector onto the z-axis. So that is r cosine theta. So this is the change of coordinates. And I want to write the metric in this new coordinate system. Now, you can do it as I had said many times. Instead of doing the exact formulas which I have given you, this thing works. The usual calculus notation, that's why that notation is used. If you just like do the regular calculus, everything works out. So I just take the dx. So I get sine theta cosine phi plus r cosine theta cosine phi d theta, and then minus r sine theta sine phi d phi. Similarly, for dy, I get dr sine theta sine phi plus r cosine theta sine phi d theta, and then plus r sine theta cosine phi d phi. And the last one is dr cosine theta plus minus r sine theta d theta. Now all you have to do is plug it back in here after squaring them. So you're constructing dx square plus dy square plus dz square. Now, when you do the dx square, you will have a term where you have a dr square, and it will have a sine square theta cosine square phi. But when you will do dy square, you get the same term but with a sine square phi. So when they add, they give you dr square sine square theta. But then you are having, when you square this dz square, you get again a dr square term, but this time you will have a cos square theta. So that cos square theta will eat up the sine square theta to give you 1. And for the dr square term, you just get dr square. Then let's look at the d theta square terms. You have r square cosine square phi, and then r square cosine square sine square phi. So it leaves you with r square cosine square theta. And then you, again, when you square this guy in the dz, you get plus, because you are squaring the whole thing, you get a plus r square sine square theta. So the thetas are again eaten up, but you are left with an r square. Now let's look at the phi square, d phi square terms. This time you have r square sine square theta, r square sine square theta, and the phi's, they are eaten up because you have a sine square phi and cos square phi, they give you a 1. So you have a r square sine square theta, d phi square, but there's no d phi term in the dz. So that's all you are left with. Now you have the cos terms, dr d theta. So you have r sine theta, cosine phi square. But from the down here, again, you have r cosine theta, sine phi square. So sine phi squares, they go away. And you are left with r sine theta, cosine theta. But from the dz, you have a minus. The cos term gives you r sine theta, cosine theta with a minus. So the cos terms, they cancel between dr d theta. Similarly, you can check the cos term of d theta d phi. That's very easy to see. They're just over here. And you have a r sine theta, cosine phi, sine phi up there and down in the second line, but with a different sign. Similarly, the cos term of dr and d phi, they also cancel. So you are left with this guy. So this is the flat metric in spherical polar coordinates. So if you were just given these coordinates and just this metric, you would probably imagine, if you hadn't seen it before, that this is some kind of a complicated space, but it's just the flat space, just written in different coordinates. We just know that there's this range, but that's okay. We're not gonna worry about those points which are left out. We weren't expecting to cover everything. Just from this figure, you can see that this is the range of these coordinates. And even the metric, you can see that theta goes from only 0 to pi. So this metric is actually, whatever calculation I have done is, one should think of it as a shorthand. But if I write it in the more formal terms, I just split these things open. This is what you have. Now, what I can do, I have a sphere. This metric computes the scalar products in my flat space. Now I say, I'm gonna consider the tangent spaces. I'm gonna, at each point, I have a tangent space. What are those? All those vectors which are tangent to the sphere at this point. And then I see that if I just consider those vectors which are tangent at this point, how does this metric looks like on those points, on those vectors? So any curve on this surface, this is how I was constructing my tangent spaces at a point in a manifold, that you consider all possible curves passing through a point and construct the tangent vectors using those curves as derivatives of those curves, and those gives you the tangent vectors at that point. So any curve on this surface at a point, suppose this is a sphere of radius capital R. So at a point, how would the point look like? R theta phi will be of the form how will the equation look like? This will be constant. because that's the very definition of the curve remaining in this surface, which for us is now forming a manifold, this surface. And then you have theta beta. They can take any form you like. As long as you keep r constant, you are within the surface. So this would mean that tangent vectors at this r theta phi are of this form. Zero, because when I'll do this thing, tangent vectors are r dot, theta dot, phi dot. So they will be of this form. So the first component is not even there. So I can just forget about it. I know that at any point it's a two-dimensional vector space. Depending on what functions I use for theta, beta, and phi beta, I'll get different vectors, but they will all be living in a two-dimensional space. Two-dimensional. They will be forming just a two-dimensional vector space because it has only these two components. So the metric induced on the surface is which computes the scalar product of these vectors. So the metric induced on the sphere is the one which computes the scalar product of vectors in tangent space using the same metric. So, but what would that be? It's the same guy. It's just that when you will give it anything over here, that's zero. That's giving you zero because it has no d by dr component. The vectors you give to it has no component over here. So that becomes zero, and you're left with the others are still gonna compute for you the scalar product for the rest of the parts. So the metric on the sphere is just this. You can write it like that in the shorthand. This is the metric induced on the sphere. And we are going to take it to be our manifold defined through this metric. Its geometry is defined through this metric. You could say, well, some people just sloppily, many things which are sloppy work. In this case, some people say, oh, I'm staying on the sphere, so I'm not changing the r. So drs are zero. And then you retain this. So it's kind of same. You could think of it, well, I think this should be enough. I'll come back to another point of view probably at the end. I don't want to waste time right now. Now, for simplicity, let's take the radius of the sphere to be 1. Doesn't matter, I can put it back in. It's just about the scale or your units. So I just take it to be 1. Then for unit sphere, my metric would be just this. In these some coordinates theta phi, which I know how do they look like as embedding. But living inside on the surface of a sphere, I wouldn't give it them much meaning than what kind of coordinates they are. They are just the coordinates in which the metric takes this form. So let us compute the Levi-Civita connection for this metric. other name for it, which is the Christoffel symbols. Levi-Civita connection or Christoffel symbols. Symbols for the sphere, or I should say this metric. Now we have G theta theta is 1, G phi phi is sine square theta. So G theta theta would be 1 and G phi phi would be 1 over sine square theta because it's just a diagonal. Now, if I start calculating, well, let me first write the formula here again. G alpha sigma d mu G sigma nu plus d nu G mu sigma minus d sigma G mu nu. So when I do theta theta theta, this theta is fixed since the inverse metric is also diagonal. So I'll have to put the theta over there. And all these things will involve thetas. But I know that the metric components of, well, they will all be like this. But g theta theta is constant. So this is 0. Then I have g theta theta phi. Let me use some other color. Theta phi. And this is half g theta theta. I first choose this theta. G, the theta comes from the summation, and I have a phi plus d phi g theta theta minus d theta g theta phi. So this off diagonal is 0. Theta g theta theta term doesn't depend on anything. That's 0. This is off diagonal 0. This is also 0. And then I have d theta phi phi. So it's half g theta theta d phi, one thing coming from the summation, one from this index over here, plus again d phi, same thing comes because I have the same symbols here. Then minus d theta, the summation index comes here, and g phi phi. So these are off diagonal. G phi phi is actually sine square theta. So I get half g theta theta is 1 over sine square theta, and then I have a minus, and when I take the derivative I get 2 sine theta cosine theta. So this thing is equal to minus cos theta over sine theta. Then I have these guys, d phi theta theta half g phi phi g theta g phi theta plus again d theta g phi theta minus d phi from the summation g theta theta. But G theta theta, they don't depend on anything. So 0. D phi theta phi is half G phi phi. Once I get G theta and G phi phi, 1 phi from this, 1 phi from summation, plus D phi G phi theta minus D phi G theta phi. Now, these guys are 0, but this is not. G phi phi is just 1. And from here, I get 2 sine theta, cosine theta. So just a sine theta, cosine theta. So again, you can very easily see that this is the last one. So they are all G phi phi. And G phi phi is they do not depend on phi. So these guys are gonna be 0. So only you had 6 connection coefficients. Out of those, only 2 are non-zero. 0 components are d theta phi phi, which is minus cosine theta over sine theta, and d theta theta phi, which is sine theta cosine theta. Now, using this, let us write the geodesic equation. Is there any question? So you have some curves defined by theta beta and phi beta, and you are solving for them using the geodesic equation. So first I write the equation for the theta. So when I write it for theta, the theta comes up there because this is this thing. So theta is going up. So right like over there. But when I put theta up there, the only non-zero ones are with the phi phi here. So I will have d phi by d beta, d phi. Well, let me write it with the tau, just because looks nicer. So this is one equation, and then I have an equation for phi. When I put a phi here, I have a theta phi. So so this matches with this d tau. But then I have the other term as well, phi theta. But these are, because the connection coefficients are symmetric and the other term is also symmetric. This is just 2 d phi theta phi d theta over d tau d phi over d tau. This is the second one. This is the first one. Now I can put in these values for these guys. So this will take this form. Minus cosine theta over sine theta d phi over d tau, d phi over d tau is 0, and d2 phi over d tau square plus 2 sine theta cosine theta d theta over d tau d phi over d tau. These things I can write them if I just use the dot notation. This theta double dot minus cosine theta over sine theta phi dot square is 0. And this I can write as phi double dot plus 2 sine theta cosine theta theta dot phi dot is 0. So these two are the equations of straight lines on a sphere in spherical polar coordinates. The coordinates which we are familiar with, which we also put on the globe. So let's call them combinedly. These two are 1 and this is 2. Now, what you could do, one thing you could do is find a general solution for these. Remember, this dot is not with respect to any of this theta. This dot is with respect to a parameter beta. It's just saying that at different points, this coefficient is changing with theta. You could try to solve them. It would be obviously extremely hard, but you could check some solutions and you can employ symmetry. I'm just gonna check some solutions now, and then I'll argue that I kind of know all of the solutions because of this spherical symmetry of the sphere, which by the way, it's not that obvious in the metric which we have just looked at. That we will see later on, that how to find the symmetries of a metric. But since you know that a sphere, we derived it from a sphere, and a sphere is spherically symmetric. The original metric dx square plus dy square plus dz square, that had a spherical symmetry because the rotations are a symmetry of that metric. We studied it in the very beginning of the course, that rotations do not change that flat metric. So that symmetry is retained in this metric on the sphere, and we will probably use that symmetry to argue some things. But what I'm doing right away, for that you don't even need to talk about any symmetry. I'm going to just check some curves and see if they are straight lines or not. So to be straight line, they have to satisfy equation 1 and 2. So consider this curve. So theta is constant. Let's say C, and phi of tau, I just put it as tau. And the question is this a straight line? So in this situation, I have phi dot is equal to 1, phi double dot is 0, theta dot is 0, theta double dot is 0. So from 1, I have 0 because theta double dot is 0, minus cosine theta over sine theta phi dot is 1 square is equal to 0. Now this is not coming out to be, this is not being satisfied. It will be only satisfied if cosine theta is 0. That means theta is pi by 2. Sine theta would be, sine pi by 2 would be 1, cosine pi by 2 would be 0, and then this equation would be satisfied. While from 2, we have phi double dot is 0, minus theta dot is 0, phi dot is 1, but that doesn't matter. So equation 2 is always satisfied for this curve. But equation 1 is only satisfied if the theta of tau, if theta remains pi by 2 throughout the curve. That means this curve phi of tau is tau. This is a straight line. But any other value, anything less, let's say pi by 4, not a straight line. So what is it telling us? That on the sphere, what is this curve? This curve. This curve is when I am at theta is equal to pi by 2, which is the equator. And I just go around the phi. So the equator is a straight line. But if I consider some circle over here, fix the theta and go around phi. This is not a straight line. Similarly, anything over here, not a straight line. So what is this equator? Equator is a what you call a great cycle. So the great cycle is a straight line, or I should probably say is a geodesic. But small cycles are not geodesics. Now this equator was one of the great circles, but if I draw any other great circle, now I'm going to use the symmetry. Any other great circle, I can think of it, I can draw a perpendicular line from the center of this great circle, which will hit the sphere, and I take this to be north axis, take this line to be the new z axis, and define the coordinates, theta phi coordinates with respect to that. They will be perfectly legitimate coordinates on this sphere. And since they are again spherical polar coordinates, in those new coordinates, my metric would still be same. So all the conclusions would be same. That would mean that this new equator, this would be the new, this would be the equator for these new coordinates, will be a geodesic. So that shows that all great circles are geodesics by the symmetry. All great circles are geodesics, but none of the smaller circles are geodesics. We can see it to another example. Well, first of all, why my drawing is so bad? If I consider this sphere, let's say I start from here. I give, let's say I start from here. I give a direction that I'm moving in this direction. So that means if I keep this direction, go around, this would be a straight line. But if I try to make a circle around like this, so then I'm not keeping this direction. I have to turn back. Instead of going here, I turn back and I make this smaller circle. In that sense, these smaller circles are not straight lines. But in any case, I mean, I get confused a lot if I try to imagine these things swirling around, which one is straight, which one is not. The best thing to do is just check the geodesic equation. That's why, I mean, uh, that's the whole point of doing maths. Equations are much more helpful than your mental imaginations. But let's check these lines. We just did lines with constant theta. Let's check the lines with constant phi. So lines or curves with constant phi, they are phi of tau is constant, let's say some c, and theta of tau is tau. Theta goes for a right, but phi is fixed. So what are these? You pick some phi here, and then theta changes like this, these lines. I can change the phi, go over there, theta goes like this. So what about these lines? So over here, phi dot is 0, phi double dot is 0, theta dot is 1, theta double dot is 0. So from 1, one was theta double dot, and it had a phi dot square. So phi dot is 0, both are 0, so 0 minus 0 is 0, satisfied. From 2, it had a phi double dot and the product of theta dot and phi dot. So this becomes 0, this product, and phi double dot is already 0. So 0 minus 0. So both are satisfied. That means all curves of constant phi are geodesics, which is intuitive because all curves of constant phi are just great circles. They are in some sense equator, or they just go from north to south, so they are great circles on this. Let us now consider the equation of parallel transport. Parallel transport on the sphere. So the equation was T mu T mu V alpha equals 0. By the way, many books, instead of this capital D for the covariant derivative, they use this symbol. So they are same when you write this. So when I open it up, this was just this. This is the vector. So what's going on? You have some curve which is defined like this, and you are computing its tangent vectors like this, and then you have some other vector v mu over here, and as you go along this curve you want to keep this vector constant, geodesically constant, or you want to parallelly transport it, and that would mean that this equation is satisfied. So this is the t and this is the v. V could be directing in any direction you like, starting, and then you just parallelly transport it. You construct a field which is parallelly transported, so that field satisfies this equation of parallel transport. So I have d by dx mu v alpha plus t mu, so I have dx mu over d tau, and gamma alpha mu nu v nu is 0. I can probably I can, so this chain rule gives me this equation. So essentially you are deriving an equation that as you move along this curve, as you change this parameter tau on this curve, how do the components of this vector v change on this parallelly transported field? How should this component be at any particular value of tau? And that is being set up to this differential equation with a variable tau. And this probably I can write back as a vector. So you feed this connection coefficient one vector of the curve and one vector which you are parallelly transporting. And this guy is already known as a field on this curve, because for each value of beta, you know what is the tangent vector over there, because you know the curve, so you can compute that tangent vector for any value of beta. So they depend on beta, and this you're trying to derive. And it's just a first order equation, coupled equations, but still first order. Well, I was calling it tau. And t is not time, it's the tangent vector. So first order equations in tau. Now, if I write these equations up, then I have d v theta. So this vector which I am transporting will have two components, theta and phi. So the equation for theta is v phi t phi is 0, and the equation for dv phi is theta phi v theta t phi plus the other way, v phi t theta is equal to 0. So let's call them 3 and 4. Now let's transport along a curve which is given by this. So let's take theta of tau to be constant and phi of tau as tau. So I'm on a sphere and I'm transporting along a curve of constant theta. So along these cycles, phi's. So start from here and transport it along here. So on this, t theta would be 0 and t phi would be 1. So all along this curve, the tangent vector is given by 0, 1 throughout. It's a very simple curve. Then these equations, in this case, so for this special case, I will have dv theta over, I am just mixing between beta and tau. Tau. So is everyone sleeping? Is
No,
anyone awake?
yes, sir.
So I just put in the value of gamma theta phi, which gives me minus cosine theta over sine theta. V phi is 0. And then I have dv phi over d tau. So this thing, t theta is 0. So this will go away. I'll have only one of these, which gives me sine theta cosine theta v phi is 0. So let's call them 5 and 6. So I have now got these coupled equations in theta and phi, and I can try to solve them by standard techniques. So one of the standard technique is that I disentangle them by going into taking another derivative. So from 5, if I take the derivative, I have another derivative. dv phi over d tau is 0. But from 6, I know what is dv phi over d tau. So I put it over here. So this gives me d2 v theta over d tau square plus, so sine cancel, cosine square theta v theta of tau is 0. This is wrong. See, this was not phi, this was theta. It was this term. And that's why you have got coupled equation v theta, and this is v theta. So they were coupled, but by replacing this, I have uncoupled them. So this is now a second order equation only in v theta. So this I can very easily solve, right? Because if I have, let me do it here. If you have d2 V over d tau square plus a square V is 0, then the solution is it. The general solution is a tau, because when I take, I get a minus a sine a tau plus ba cosine a tau. I take another one, I get minus a square a cosine a tau minus ba square sine a tau. So I can take this minus a square common, and I get my original V back. So I satisfy my equation. So that means this is the solution. So this would mean that V is a cosine, V theta is a cosine of cosine theta beta plus B sine of cosine theta tau. Cosine theta is a constant as far as tau is concerned. It's just a coefficient over there. So then you can then find V phi directly, because V phi from this equation, from 5, I just have to take a derivative. V phi is sine theta cosine theta d by d tau of V theta. So it's minus sine theta cosine theta a sine of cosine theta tau plus sine theta cosine theta comes out because of, again, a derivative. Tau. So finally I have V of phi. Let me use some other color. Minus sine theta I can take common. A sine of cosine theta beta and minus B cosine of cosine theta beta. So you can see that as I move along the curve, as I change the beta, these thetas, they change. They do not keep pointing. So if I'm over here, your intuition might tell you that if this is pointing in, if I start with this vector, V theta is 1 and V phi is 0. It's this vector. Its only component is along the theta direction. Well, this actually has a minus. V theta is minus 1. So when I go over here, I do not come to this one. It swirls in weird way. Because of this sine and cosine, it has some swirling. But because it has, these components are sine and cosine, once you come back after 2 pi, you always have the same vector back in here. Actually, you can derive that what is the periodicity. It's actually going to be something different, but at 2 pi it certainly is periodic. But if I check at theta is equal to pi by 2, then cosine theta is 0. This thing is 0. So sine of 0 is 0, and I have this thing, this cosine of pi, this is also 0, so I get a uh, uh, I get v phi is minus sine theta plus b, and sine theta is what? It's 1. So I get a b cosine of 0, 1. V phi is just b, just a constant. Similarly, v theta, I have a 0 here, and cosine of 0 is 0, is 1. So v theta is a. So these were the initial conditions that what, well, you could have checked. I should have told you that how to find the initial conditions. Well, you know these equations. So if I start from tau is equal to 0, the initial condition is v theta is a and v phi is b at tau is equal to 0. So because we know from general theory that these are coupled first order differential equations, if I give both of the components an initial value, I have a solution. I have a particular solution. So this is what we find, that at tau is equal to 0, you have v theta is equal to a and v phi is equal to b. You can choose these a and b and then transport any vector you like. So if I transport any one of them, I find that on the equator, it does not change. So if I start with this, v theta is 1 and v phi is 0. So this guy pointing upwards along this circle, this great circle. So when I move it to any other position on the equator, it will again be pointing towards an increasing theta line, going towards the north pole. Will have no component in the phi direction. So this is what we mean, that when we parallelly transport, we go like this on the equator. But on the other smaller circles, it's much more complicated. It takes a full circle. As you rotate, it takes a circle and comes back. It swirls around. Now let's take this curve. Now let's uh, transport a vector along some other curve. T theta is equal to 1 and T phi is equal to 0. So I'm taking this vector and then now I'm trying to transport it up like this along a curve which has a constant phi but some theta. So in other words, I transported it over here. Now I want to take it up there. So the equations would be dv theta over d beta plus gamma theta phi phi v phi and t phi. This is the first equation. But t phi I have taken to be 0. So this whole thing becomes 0 and I get dv theta over d beta is 0. And the other equation is dv phi over d beta plus gamma phi phi theta v phi t theta is 0. So dv phi over d beta plus sine theta cosine theta v phi is equal to 0. So if I take, for simplicity, if I take this vector, well, this only changes the norm. Theta doesn't change. This equation says v theta remains constant. V phi changes, but if I can kill this complicated equation by assuming that I start from this. So this vector, which I had transported over here, then this equation, this becomes 0, and this equation also says is 0. So that means v theta and v phi both are constants. For this starting vector, and a curve of constant phi. So that means if I take it up there, it will just go like this. It will keep pointing along the increasing theta, and it will be on the north pole, it will be like this. But that also means this is also a curve of constant phi. So I can transport this like that. And my equations tell me that its components at any particular point. So at each point, I have to look at the curves, look at the basis vector. Over here, the phi basis vector is in this direction and theta is in this direction. So it keeps going like that. So what I find that when I transport it over here and take it back, it points in this direction. But when I transport it along this curve, it points in this direction. So they're not pointing in the same direction. They're not same vector when you rotate them around a curve. This actually turns out to be one way to check if there is curvature in the underlying space. Take a vector and transport it along some curve. Well, you could think of it in another way. So since I have explicitly computed how to transport vectors along these special curves and this special vector at least. So if I take it like this, it will come here. I bring it over here. Then I can try to pull it back. I'll find that it points like this because I know how this guy goes over there. It doesn't match. So this turns out to be a definition that you go in a closed loop in your space, and if you do not come back to same vector, if you rotate, this is called the holonomy. This is one way of checking the curvature, if there's any underlying curvature in your manifold. Now, what else I had to say? So next time we will try to quantify how to tell that if some manifold, if we are given a metric and we know that we are only dealing with Levi-Civita connections. So we are given a metric, so we know what is the connection, but we don't know what coordinates are being used. We live on the manifold. All coordinates are equal. Coordinates do not tell us anything. So we are given some components and of the metric, how to tell if this metric is curved or not. To go towards there, maybe I think I should stop. I shouldn't discuss that today, except let me just make a statement, which we will show next time. that we will find that it is always true that if you have any metric in any coordinate system on any manifold, you can change coordinates so that in new coordinates, this your metric components are equal to eta mu nu at one particular point. So no matter if you are in curved space or not, even if you are in curved space, your metric, if you are in curved space, that means there will be no coordinate system in which metric is, well, this is not visible at all, in which metric is eta mu nu in a neighborhood. You take some paths, some coordinate paths, your metric will not be equal to eta mu nu if this path is flat. But at a point, you can always do it. No matter what kind of manifold you are, even if it's curved, at a point, your metric can always be made equal to eta mu nu. At that point, the metric components will be this. So on that vector space, at that point, you can take the scalar product of vectors on that TPM using the ordinary eta mu nu. Or this is for Lorentzian, but if you are taking the other signature, then this is just the Euclidean. You can use Euclidean scalar product at one point. Well, you can do it at any point. So you can construct this change. You can pick out the basis so that at any point you can use the Euclidean scalar product. But the point is that there will not be the basis vector of any coordinate system. But you will be able to find a coordinate system so that it happens at one point, but it won't be happening at nearby points. Not only that, you can also get things arranged. You can find the coordinate system where this happens, and at the same time, this also happens. That the first derivative of the metric is 0 at that point. But obviously, if you have all the derivatives equal to 0, then it's constant. So all derivatives cannot be equal to 0. You find that you cannot arrange. This cannot be put equal to 0. The second derivatives of the metric components you will not be able to put to 0 if the manifold is not flat. So we will prove this kind of very easy. It's just application of Taylor series, this theorem. And this is a consequence of the fact that locally the manifold looks like a flat space. It's just a consequence that we have created the manifold by patching up the RNs. And this fact that you cannot put the second derivative is equal to 0, this will lead to what we call the Riemann tensor. And this failure for the second derivatives to be 0, it is captured in this tensor, and it's a measure of curvature. And these coordinates where these things happen, that the metric is equal to the flat metric at one point and the first derivatives are 0. These are called the Riemann normal coordinates. So we will see these things next time. Okay, should we stop here?
Okay, sir.